Today, we're going to talk about hash tables. This is our introduction to hash tables. So if you've not heard of these before, then this is a good place to start. We've seen a lot of data structures thus far in our class, and if we were designing one from scratch, what kind of properties would it have? Well, it's pretty clear that what we might want is constant time operations for all the relevant functions like insert, remove, and query. And if we look at and think about other collections that we've seen, if we have an array or a list, finding something in that array or list requires order n time because we have to search through everything. It might be simple and easy to put something in there, but finding it again, unless it's kept in some order, takes linear time. In order to improve that query time, we turned to balanced search trees. And balanced search trees have log n query time. And that's due to both the fact that we're ordering everything in the tree and balancing while we're doing that. So we took something that was unordered, like an array or a list, we imposed order and balance, and we achieved log n query time. Now, hash tables take a completely different approach. Hash tables are actually able to achieve constant time operations for insert, remove, and query in many real world situations. But the real question is how. And strangely, even though when we were moving from arrays and lists and the like to balanced binary search trees, we imposed order in order to improve our runtime. Hash tables achieve a speed up by not imposing order in quite this way. In fact, if you look at how a hash table arranges its data, it seems to be almost random. Kind of like, I like to give the example that you know how your bedroom is laid out, and your bedroom might not be the cleanest thing in the world. Maybe it is. But you might have a pile of clothes in one corner and a pile of books in another corner, and when you want to find your favorite shirt, it might be in your drawer, it might be in one of these piles, but you know where it is, but it's not necessarily in a particular place every time. Um, but knowing where it is and having the ability to recall where it is very quickly allows you to navigate your room very quickly, even though the contents of your room might be a ridiculous mess. And in a similar fashion, a hash table kind of puts things all over the place in no necessarily discernible order that we can easily discern, but because of that, actually, because of that seeming disorder, it actually can achieve very good performance. Um, but that order one time is not guaranteed in all situations. So I wouldn't always say that a hash table is always constant time, but with good planning and good uh, preparation, you can achieve this in the real world. Okay, so what is a hash table? Well, it has three parts. The table portion is actually an array, and we also need its size, which we'll call in this lecture, we'll call this table size. We also need a hash function. A hash function is the thing that tells the hash table where to place something, or at least an indication of how to know where to place something. And the third part that we need for a hash table is something called a collision resolution strategy. And we will mention that today, but we won't get to talk about that today. But today we'll look at and talk about these first two parts. So the thing that makes a hash table fast is the hash function. And the hash function has an input, which we call the key. And this input could be whatever it is that we want to store in the table. However we want to look up things in the table, that's what we're giving as input to the hash function. So this could be an integer, it could be a string, it could be a person, whatever that we're storing in the table. And the output from the hash function is a non-negative integer. So it could be 0, but it's usually a non-negative integer. And this output is used to help the hash table place the object that is being hashed. And when I say placed, I mean either put it in when we're inserting or find where it is when we're querying or removing it. And some properties of the hash function is that it, of course, should be fast. It should operate in constant time because if we need to find something, we need to operate quickly. And when we say constant time, we usually mean constant time with respect to the number of things in the hash table already, of course, but also hopefully constant time with respect to the size of the object that we're hashing. But that's a longer discussion. But it should be a fast operation. Another important property is that it must be deterministic. What do we mean by deterministic? Well, simply that for the same input, the same thing that we're giving as input to a hash function, the hash function should always return the same integer as output. Okay, so this is like going back to the analogies I said before. If you're looking for your favorite shirt, well, maybe you know that it's always in the pile that's next to the door of your room. Okay, so the input is the shirt that you're looking for, your favorite shirt, and the output is the pile next to your door, and that's always the same. Another way of putting this is that the hash function might involve some randomness, but the actual output of the hash function should never be random or change with respect to the input. Okay. Otherwise, we can never find anything again that we are looking for. So I guess one more point on this is that even though the hash table might seem like, as we said up here, we might seem like that the hash table's entries are not in any easily discernible order, that things seem out of order. There is, in fact, an order to them, and that order is determined by the hash function. And the hash function has to return the same value for everything, otherwise we won't be able to find it again. Okay, so now that we understand what a hash table is, it's an array or a table, and the hash function itself, we can give some quick and what I'll call incomplete implementations. And they're incomplete because they don't take into account all the things that might happen, which we'll talk about later. In fact, mostly in the next lecture, a little bit today, and a little bit and more in the next lecture. So the insert function for a hash table might look something like this. And this is just pseudocode, so don't worry about the details of this. If we wanted to insert a key called k, the first thing that we need to do is compute the hash function result on k, and we get a non-negative integer called h. And then we'll use h to find an entry in the table and assign that entry in the table the value k, or the key k. Okay, so insert is as simple as doing the hash function lookup and then putting it at the table. Now, the one key thing here is notice that we're taking that hash value and we're computing it with the modulus of the table size. So that guarantees, since the hash function returned to us a non-negative integer, that guarantees to us that the tables, that the entry that we're looking at is somewhere in the table between 0 and table size -1. Okay. Then query is similarly simple. We hash the key and we just return the key that, or the entry that is at that table, slot in the table. And then similarly for remove, notice I have some sort of weasel word here, remove that entry of the table. We'll talk more about how to actually remove later, okay? But we just basically, it's the same idea. We hash the key and then we get rid of the item that's at that table entry. And so the analysis of these three methods is that if the hash function is constant time, which it should be, because it actually doesn't have anything to do with the number of entries already in the table, then all three of these methods, insert, query, and remove, are also constant time, or so it seems. But there is a catch, and we'll see what the catch is in just a minute. But first, let's do an example, okay? So let's pretend like we're going to build a hash table of ID numbers, student ID numbers, okay? So the key that we're going to hash is an integer itself. And let's assume that this is not just an integer, but let's assume this is a non-negative integer, okay? The table size is 7. The hash function is just the identity function. So in other words, given a non-negative integer, just return that same integer. So that's an extremely simple hash function, and it works well for our first example. Now let's do an example. Let's do an example where we insert the following ID numbers into this table. Okay. So the first thing that we're going to do is we're going to insert 0. Well, hash of 0 is 0. Okay. So 0 is the output of the hash function. And 0, we need to take that and modulus by the table size, which is 7. So 0 mod 7 is 0. So we would insert the key 0 here. By the way, you'll notice that I've put dashes here. And as I like to point out, it's not that there is nothing at each of these entries in the table. There are entries here. I just don't care what they are, and I'm using a dash here to indicate the fact that I don't care. But the bits here are very much alive and well, and there are integers at these entries. We just don't care what they are at the moment. Okay, moving forward, let's insert 5 now. Inserting 5, we take 5, and the hash function of 5 is 5. Modulus 7 is still 5, so we would put 5 as the key at entry 5 in the table. Moving on, if we hash on 18, the hash function of 18 is 18. Modulus 7 is, you guess, that's right, it's 4. So at entry 4, we're going to store 18. Next, a larger number, 491. 491 is returned by the hash function. Modulus 7 is 1. So we'll put 491 here. Finally, we'll insert 19. 19 is returned by the hash function because the hash function is the identity function. Modulus 7, so 19 mod 7 is 5. And we want to put 19 here. But guess what? Entry 5 in the table already has is already being used for the key 5. So who gets to use it? 5 or 19? Well, we want to keep both of them. And so what we've just encountered is our first catch. The first catch is what's known as a collision. Okay? A collision is when two different keys hash to the same location. And that's what we just saw. When 19 and 5 both hashed to entry 5 of the table, then we need to be able to store both of them. We don't want to just discard one of the two objects or multiple objects if they have the same hash. So we need a way to resolve collisions. And as I mentioned earlier, we'll fix this, we'll address this in a future lecture. We won't fix this today. For now, we'll just assume that hash tables work, and we know that collisions can happen, but we'll figure out how to deal with them later. If collisions didn't exist, then all hash table operations would be constant time for the reasons that we've already explained. But we do know that collisions will happen. We just saw one. We saw one because two different keys can both hash to the same slot. But we can practically guarantee that this will always happen, especially for a fixed size table. And this is due to the pigeonhole principle. The pigeonhole principle tells us that we can't stick more than n items into a table that has only n slots. So for example, if you were going to try to put more than 7 items in the example table that we were just using, you couldn't do it without resulting in a collision. So even if we hadn't had a collision up to the 7th insert, after we've inserted 7 things, we are guaranteed to have a collision. So collisions must be dealt with. They can and will happen. We'll figure out later how to deal with them. And actually, the collision resolution strategy is the primary reason why hash tables are not guaranteed to be constant time. The second catch that I want to point out is, how do we know when a hash table entry is being used? In other words, if I went and queried this hash table above for, say, index 4, how do I know that 18 is actually being used versus at index 3, there's nothing there? Well, you say, well, there's a dash right there. But as I explained earlier, the dash is just a visual placeholder for this lecture. There actually are bits there that represent a real key. So how do I know that that entry is free and that entry is being used? Well, again, we'll address this later in a later lecture. Okay, we're going to have some extra machinery for keeping track of which entries in the hash table are actually being used. But for now, it's sufficient to talk about them as if we knew what those were. Okay, moving on, I want to talk about what if the thing that we want to hash is not an integer. So for example, we might want to hash strings. The hash function just has to work on the type of the key that we're hashing. And so therefore, if we want to hash integers, we need a hash function that works on the input of integers. If we want to hash strings, then we need a hash function that takes as input a string. The output of every hash function is always a non-negative integer. That's always the same, but the input type might be different. So we need, for different types that we might want to hash, we need to have the ability to hash them differently. So we have to have, you can't have one hash function that works on sort of every type. You have to have different hash functions for different types. Another minor point I want to make is that hash tables, in the example that we just did, we treated a hash table as a set. What is being stored is just the key. So the ID numbers, all we're storing were the ID numbers themselves. But we could also treat a hash table as an associative array, or you could call it a map, where each hashed key has an associated value. This is like the difference between an STL set and an STL map, or a standard library set in C++ and a standard library map. But what is the same between these two interpretations, whether we're treating a hash table as a set or as an associative array or / map, is that what we're hashing is the key and only the key. And an associative array or a map might have a value that tags along, but that's not used in any way for searching the hash table. Okay, so the hash function is still on the key. Let's do another example which combines these two new ideas of non-integer types and associative arrays. Let's build a DNS, a domain name server. Okay. So a DNS is a type of server that sits on a local internet and does things like maps from the name of a server to an IP address. So the key here that we're hashing on is the domain name. Something like when you type into your web browser www.baylor.edu, how does your computer know how to get to the server that corresponds to that domain name? Well, your computer might know what IP address that is because internet traffic is routed by IP address, not domain name. Domain names are simply some syntax that we've added on top so that we can keep track of human readable names for computers. And so the value is an IP address that we want to actually use, and we need to look that up. So a DNS is a computer that lives on the local network, which has the ability to answer queries like, what is the IP address for www.baylor.edu? And replies with something like 129.62.5.220 or something like that. Okay, so we'll build a very, very simple version of a domain name server. And again, this is an associative array or a map now because we have both a key and a tag-along value, and we want to be able to hash and look up things by the key, which is the name, the domain name. And the result that we want out of our table is the value itself, the IP address. Our table size will be the same, it'll be 7. The really interesting part here is how do we do the hash on a string? Well, we're going to do a very, very simple hash here. It's not necessarily a good hash, but it's one that we can work through in this lecture just to give you a taste for how this might work on hashing a string. So the hash function here takes as input a key k. That key is a string, its domain name, and it's simply going to do the following. It's going to take the first character, multiply it times 101, and then add in the second character. So it's only going to look at the first two characters. And while we're doing this, you'll notice that since we're doing multiplication and addition, we're actually treating the property that in most programming languages, C and C++ in particular, you can treat the characters as integers and multiply and add them together. And as a hint, we'll take the, I'll note that the ASCII value for A is 97 in decimal. Okay, so here's our table down here. Let's just do 2 insertions. We want to insert www.google.com and mail.baylor.edu with these associated IP addresses. So we're going to insert www.google.com and mail.baylor.edu with their associated IP addresses. And again, the keys will be stored here, the values here, but we're only hashing on these string keys. So let's do the first one, www.google.com. Well, the first 2 characters are ww, and so we want to take the ASCII value of w, multiply it times 101, and add the ASCII value of w. So what is the ASCII value of w? Well, I don't know. Let's look it up. So the decimal ASCII value of w is, let's see, right here, 119. Okay, so we need 119 times 101, that's 12,019. We'll do that plus another 119, that's 12,138. Now, that's not the value we want to use for our insertion. We want that modulus 7, and that gives us 0. Okay, so at this location, at index 0 in our table, we'll put www.google.com with the value of 172.217.9.4, which is what it was when I looked it up earlier today. Okay, so we've stored 1. Now, let's do mail.baylor.edu. So again, I need to know what is the ASCII value of M, the decimal ASCII value of M, and here it is. It's 109. Okay, so I'll do 109 times 101 plus 97, all mod 7, and that gives me 4. Okay, so at table index 4, I'll put mail.baylor.edu with the value of 129.62.5.225. Okay, so we have no collisions, but that's not the point of this. The point of this example is simply to show you a way of computing a hash function on a string. And as I said, this is a very simple, very fast hash function, but it's not necessarily a good hash function, especially for this application. Can you think of why? And I'll pause here to let you think of why. Well, if we're hashing domain names often, but not always, start with ww, right? So this hash function would result in the same hash value for every domain name that starts with www, whether that's www.google.com or www.baylor.edu, and so on. And so that is very likely to happen. So consider the distribution that we have of domain names. It's very likely that that's going to happen. How do we combat that? Well, we can combat that by integrating more than just the first two characters when we compute the hash function. The other thing I want to point out with this example is the fact that we're multiplying times 101. Why are we multiplying times 101? What does that do for us? And why this particular value of 101? Well, one thing I'll point out about 101, which we'll come back to in a later lecture, is that it's a prime number. But the core reason why we want to, and the prime number factor, the fact that it's a prime number is going to be important later. But the really important thing is we're going to we're going to multiply by the first character and not the second character and just add them in, because that allows us to distinguish between two domain names that begin with the same two letters but in a different order. For example, if I had a domain name that started with am something something something, if I didn't multiply by 101, if I just did a hash function that was like this, just add the first two characters together, then guess what? MA and AM would produce the same hash value. But because we're multiplying times 101 on the first character, but not the second, these two will produce different values, and then we add in the second value. So the multiplication here allows us to indicate some difference in these characters by their order. And so that'll turn out to be important. If we wanted to make this better, we might loop over all the characters and keep multiplying what we had as our hash value by something like 101 and then adding in the new character. Okay, so let me just briefly give you an example of what that might look like. You might do something like hash on k would be something like for ki in, or let's say for I in the length of k, we'll start with a hash value of 0. We'll say hash value gets hash value times 101 plus k sub I, and then return hash value. So this does two things. First of all, it looks at all of the characters in the string, and secondarily, it uses this multiplication trick to sort of move out of the range of the new character that we're adding in the old hash value. Okay, so this allows us to take order into account. Now again, this is not a perfect hash, but it's much better than just using the first two characters. Okay, so I just want to make a few more comments in our discussion today. And the first is, what are our considerations when we're building hash functions? First of all is the type of the key. Is it an integer, a string, a person? What is it? That's going to determine the method of the hash function. The second thing is, what is the allowed complexity? Well, we just saw a hash function which took two characters out of a string versus a hash function which takes all the characters of a string. And if the string is very long, then that second version might take a long time to run. So we have to balance the amount of time that it takes to run with the quality of the hash function. And the third point is, what is the distribution of those keys? We just saw that if you take the first two characters of a domain name, they are quite likely to be WW. That doesn't happen in most strings in the real world, but in domain names, it is very likely to happen. Okay, so the point here is that a hash function that is good on one distribution of keys might do very poorly on another. So let me take a simpler example. For example, suppose we're hashing integers, and our hash function is again the identity like we saw in the first example, and our table size is 1,000. And 1,000 is a pretty bad table size, as we'll talk about in a later lecture, but for this purpose, let's use that. This is a good hash function if the keys are randomly distributed. It's a bad hash function if the keys are all multiples of 10. Can you think of why? Well, the reason that it's bad if the keys are all multiples of 10, in other words, this is a bad hash function, is because we will only be using the entries of the table which are multiples of 10 themselves, because we're going to take the key as its own hash value and then mod it by 1,000. So we'll use, and since the keys are 0, 10, 20, 30, 40, 50, 60, and so on, up to and past 1,000, but they're all multiples of 10, we will never use entries 1 through 9 or 11 through 19, and so on. So we would waste 90% of the space in the table. Okay. A few more comments. What makes a good hash function? Well, we've already talked about the fact that it's quick to compute. The second property that makes a hash function good is that it should distribute the keys uniformly across the table. And what I mean is that it should be no more likely that any one table entry gets used than any other table entry for any randomly chosen key. And finally, as we've seen, it should not be strongly dependent upon the key distribution. So where which parts of the table get used should not be strongly dependent upon how the keys themselves are distributed, as in the example that we just saw. Okay. Last thing for today, for this lecture, is I want to define the term load factor, which we'll use in upcoming lectures. The load factor is very simply the number of items in the table divided by the table size. And we give the load factor the Greek letter lambda as a notation. Okay, so we'll use this later in our analysis, but it's a very simple definition. And I'll just show you real briefly, lambda is the Greek letter which looks like this. Okay, so it's the number of items in the table divided by the table size. Okay, so next time we'll talk about how do we deal with collisions and how do we deal with the fact that we don't know whether or not an entry in the table is actually being used.